Good morning. Today we're going to talk about matching derivative and regular function graphs. And so I want to start off by just going over kind of a brief demonstration here. So some things that we know is we know basically how to graph regular functions. Now I could use an XY table, I can use a graphing calculator to graph this, but essentially it's going to look like this. It's going to be a cubic function that's going to increase, it's going to have a root at -1, it's going to increase to 4, and then it's going to come back down to a minimum at 2, and then go back up. So there's our function. All right, now, when we take the derivative of that, we can just use the power rule, right? Move the 3 down, take 1 away, move the 2 down, take 1 away, and that 4 would become a 0. So this would be our derivative. Now, if we were to graph our derivative, obviously it's not going to look the same. Our derivative graph is going to look different. And when we actually graph our derivative, what it's going to look like is something like this. This is actually going to turn into a quadratic or a parabola, right? Well, because it went from the power of 3, a cubic function, to the power of 2, a parabola. Now, these graphs are definitely different. Now, what we're going to be asked today is how do we just, without the functions, match one graph to the other, knowing just that maybe if this is the derivative graph, how would I know what the original graph looked like? So we have to use some basically key annotations. All right, so one thing that I would kind of look at here is anytime that there's a maximum or a minimum, okay, max and min are going to have derivatives of 0, right? So we know that this is a tangent line, so what does a derivative of 0 look like? Well, that means the slope is going to be 0. That means the output in this function is going to be 0 here and here. So notice wherever there's a max and min, we actually have x-intercepts in our derivative graph. Now there's a lot of things that we could look at here. Another thing we could look at is obviously this is concave down to concave up, and it changes and it has an inflection point somewhere in the middle, right? And we can see that that inflection point is actually right here when our derivative graph changes direction. All right, so there's a lot of things that we can notice here, and that's where this is going to be really, really helpful. All right, so that you don't have to memorize all of these things. You can just look at this chart and just remember that if the original graph is increasing, the derivative graph is going to be positive. And what I would look for there is I would just look for that graph to be above the x-axis. Actually, let me write that in blue as well. And that's going to be above the x-axis. So just a visual of that. Wherever the original graph is increasing, see how this entire thing is increasing? That means from -infinity to 0, my derivative should be above the x-axis, right? Right here. Boom. Okay. If it's decreasing, we know that the derivative is going to be negative, and that's going to be below the x-axis. The max, okay, we know that the max and the min both have derivatives equal to 0. And we also know that that's going to look like that's going to be on the x-axis. But how would we determine if one is a max and one is a min? Remember that a max goes from increasing to decreasing, right? So that's going to go from positive to negative. And what that looks like is above to below. And conversely, this is going to be a negative to a positive, right? Because if you think about a minimum, that's going down, then up, and that's going to be below to above. So let's just double check on our graphs below. All right, so this was a maximum. So this went up and down. So this max here, let's see what that looks like over here. Not only did it hit the axis at 0, it went from above the axis to below the axis at that point. So that made me understand that this was a max here. Okay, and then for this, there would be no minimum because even though it touches that again, it does not go below the axis. Okay, so concave up is going to be anytime we have a increasing derivative graph. So that's going to be like going up. So let's just take a look. Well, let's just fill out concave down real quick. That's going to be decreasing and going down. So let's take a look. Concave up is going to be increasing. So We can see that this is concave down here, so that must mean that it's decreasing from -1 to 1. Let's see. Is this graph decreasing from -1 to 1? Absolutely it is, right? And then it's concave up, it switches from 1 to infinity. Boom. Okay, then it turns to increasing there. So just kind of looking back and forth and comparing, and then our inflection point is going to be when the derivative's derivative, so the derivative of the derivative, think about the second derivative, is equal to 0. And our annotation here is we're going to be looking for a local min or max on our derivative graph to actually find our inflection point on our original. Now I hope that clarifies some things on kind of the difference between those two and how we can use one to find the other. All right, and then lastly, we're going to go to kind of a matching activity here and kind of figure out how can I use one graph to find the other. And in this graph, I'm only going to give you your f prime of x. So it's going to be really handy to have this in front of you. This is like double starred. I would not be able to live without this during this lesson. Make sure that you have that next to you while you're solving this. So we want to know which of the following could be f of x. Now, we kind of just talked about one with a cubic and a derivative, so that might give you some hints. But remember that this is the derivative graph. Okay, and these are going to be the originals. So let's just kind of mark up some things here. I see that I have derivatives of 0 at -1 and 1. So let's just know, what do we know about if something is a derivative of 0? If the derivative is 0, that must mean a max or a min. Okay, so these have to be max and mins. So not only do I know that these are max or mins, let's actually figure this out. This is above to below, and I can see that above to below is going to be a max. So right away, I know that this is going to be a max, and this must be a min from below to above. So that's the very first thing that I would notice, is I would look at those points right there and see if anything has a max and a min at -1 and 1. See, this does not have a max and min at -1 and 1. Those are actually roots, so it can't be A. B have max and min at -1 and 1. Okay. D and E do not. Now let's actually make sure that those max and mins are correct. Let's see, is there a max at -1? Yes. Is there a max at -1? No, that's a minimum. So just with that key annotation, now I got kind of lucky by looking at that information first, but I was able to kind of decode this problem just with that one annotation. Other annotations that you could see here, and let's just kind of continue to break this down. We are above the axis here, so that must mean that if we are above the x-axis for our derivative, that must mean our function is increasing from -infinity to -1. Sure is. Okay. And it must be decreasing from -1 to 1, so it dips below the axis from -1 to 1. Okay. And then it starts to increase again. Okay. Take a look. Make sure that you have this in front of you today. Use it. This is going to be the most helpful thing.